So today, before getting into the actual deck, so I'd like to say about myself. So I'm working as a software engineer in Minneapolis, working with Best Buy, and today I'd like to go over uh, the real-time security analytics in data lakehouses using Apache Iceberg and event streaming platform using Kafka. And so the challenge that we are talking about the traditional SMEs, why they are too slow, and for the modern threat landscape and the latency, what we are measuring in hours rather than seconds. And the solution that we are looking for is using Lakehouse native security analytics, leveraging open source stack like Iceberg, Kafka, Spark, and Arrow for real-time detection. And the results are proven already with 10 billion plus events every day and 99% of the latency reduction, enabling large-scale behavioral analysis. So this approach treats security telemetry as first-class and real data, offering a scalable, cost-efficient, and cloud-agnostic security architecture that reduces detection time from hours to the seconds. And going to the next slide. So the security challenge that we are facing with the growing complexity and manual incident response is too slow for the today's attack speeds. So the opportunity that we are taking is leveraging the lakehouse metadata for proactive security and unified visibility across AWS, Azure, and GCP. So the limitations that we have with traditional approach these as of now. So the latency issues. So where SIEMs are ingest logs late, resulting in 4 to 6 hours delay that leave organizations vulnerable during the critical attack windows. So and it comes with cost constraints, high storage and compute costs limit retention periods, making historical analysis expensive and often impractical. So the query performance, the querying historical logs often takes hours, preventing rapid forensic investigation and incident response. So the limited intelligence that we got we cannot handle petabytes scale of events ingestion and lack of machine learning or behavioral context for the sophisticated threat detection. So the soil systems often separate from the main analytics ecosystem, resulting in soil insights and inconsistent schemas across the providers. So with that, we are getting into the Lakehouse opportunity where we are getting unified batch streaming and historical analysis in a single platform, providing the foundation for next generation security analytics. So the unified architecture that we are talking about, it combines batch streaming and historical analysis with the ACID guarantees and schema management through Apache Iceberg, and the time travel capacity, enabling auditors to replay entire breach and perform the forensic analysis without restoring the backups. So it is ML ready structure, metadata rich structure, ideal for ML based anomaly detection and behavioral analysis at scale. So it is cost efficient too. So the lower storage cost than traditional log retention systems while maintaining petabyte scale capabilities. And the cloud portability, open source and portable across all cloud infrastructure, enabling continuous real-time write plus read without contention. So the system architecture in general looks like this, where we have ingestion, the ingestion that we use Kafka for high throughput, even streaming with NiFi Kafka Connect, normalizing the audit logs from multiple clouds, and the processing. We are using Spark structured streaming platforms, stateful anomaly detection with subminute latency, and storage. Iceberg tables stores the raw and enriched security events with ACID guarantees and time travel. Query and alert, a multi-engine query layer with Airflow orchestration for automated alerts and incident workflow. So this is the architecture for the system, which will build for horizontal scale out and multi-region deployment. The end-to-end pipeline ensures sub-minute analytics across petabyte scale workloads without interrupting production systems. And so to normalize event ingestion, we are using cross-cloud integration. The system integrates ingest security telemetry from CloudTrail, Azure Activity Log, and GCP audit logs, and apply them to schema mapping to ensure unified structure across all providers. So it is version transformations, allow safe schema evaluation, buffering handles late arriving or out of order events, real-time enrichment with IP, reputation, and geodata, consistent timestamp alignment across regions, reliable exactly one semantic end-to-end. And unified security event schema looks like this, where identity and context, we will be using user role and authentication for metadata, network data, where IP addresses, geolocation, and source information will be captured, and the resource details, target system, services, and data assets will be captured, operational info, the actions performed, and query of metadata and outcomes will be provided for the unified security event schema. Along with that, we will have statistics, statistical fields, where bytes stands number of bytes stands for rows accessed and duration of metrics for the machine learning to understand. So this will fully denormalized model. This is a fully denormalized model is for optimization for query speed, with Iceberg evolution allowing field for additional without downtime. Schema consistency simplifies cross-cloud analysis, while snapshot metadata enables accurate lineage tracking and correlation with workflow logs. So forensic analysis, where we can query data any moment with Iceberg snapshots, it will enable us to query any past movements in time without restoring backups or duplicate logs. And we'll be using trace attack chains. Investigation can trace attack chains from start to finish, reconstructing exact user behavior during the compromised periods. So comparing the states, enabling comparison of before versus after breach states with guaranteed data immutability for evidence preservation, and support compliance, support regulatory audits, including SOX, PCI, DSS, GDPR, and other compliance frameworks. So where we can go to real-time anomaly detection. We will be using a multi-layer detection, the system which can combine statistics baseline, rule-based detection, and machine learning to identify threats in real time. So where the baseline compute will get for per user, resource, IP, and the time window. We can use the statistical models to identify deviations in real time, and we will be detecting signatures through rule-based detection, and we will be getting high accuracy for the multi-factor anomaly. So these threat categories detects excessive data transfer, privilege escalation, lateral movement, and suspicious access pattern with enriched alerts containing context and severity. So partitioning and performance. So we will be getting time-based partitioning, efficiency, time range, queries with automatic partition, pruning for later faster analysis, identity bucketing, where bucketing is used for source identity, prevents data slow and improves query performance. And we will be using hidden partitioning, columnar format, arrow fight, and metadata management for the partitioning performance tuning. The case study with the Fortune 500 deployment, it has found that there is 150 petabytes of data transferred across multi-cloud environment with 6 regions with 10,000 plus internal and 50,000 plus external API users. And there are events of 115K events per second at peak ingest rates. And alter latency, real-time alerts within 5 to 10 seconds for critical threats. Compensation ratio, dramatically lower storage cost. So it is giving us end-to-end detection and reducing 4 to 6 hours of window to 1 minute or less than 1 minute. That is fully integrated with IAM and compliance systems. So the detection results. So around 847 results have been flagged, which is giving the impact analysis, genuine threats, prior detection rate, and faster forensics. This is all that we are getting through the faster detection. And the challenges and the lessons learned from this problem is the multi-cloud normalization. Normalizing multi-cloud telemetry was the hardest challenge. requiring extensive schema mapping and transformation logic. So, which we are getting baseline tuning, baseline need to continuous tuning to avoid the false positives. Early deployment suffered alert fatigue, later improved with ML. And metadata management. Iceberg metadata compaction require regular scheduling to maintain optimal query performance. Access control. Cross-engine across control solved using Apache Ranger for unified security policy enforcement. Governance. Schema governance is essential to avoid downstream breaks and maintain data quality across the teams. Observability. Distributed pipeline observability critical for troubleshooting complex multi-stage processing issues. So these are the challenges and lessons learned. And the future direction conclusion, the future direction is with ML enhancements, where isolating the forest, graph neutral networks, and sequential model for more sophisticated threat detection. Federated learning enable privacy preserving analysis across regionally isolated datasets. SIEM integration, where enhanced integration for hybrid enterprise environments combining lakehouse and traditional tools. Automated response. So content scoring with human in loop workflows for intelligent threat remediation. So the conclusion is Lakehouse native security analysis delivers faster, cheaper, and smarter for threat detection. This architecture bridges SIEM gaps while enabling the deep forensic capabilities proven at petabyte scale multi-cloud environments. So it represents a fundamental shift towards defining data platforms that detects the security and first class analytical capability, which will provide for the system throughout. So that is the conclusion, and thank you so much, everyone.